Okay, continuing on with 1.2, we're going to talk about boundedness. So the idea of boundedness is conceptually similar to extrema. Let's take a look at the concept from a graphical viewpoint. So just think about it. What does it mean to be bounded? Or what's a boundary? A boundary is a line you don't cross, right? So if our graph is going to be bounded, there's going to be some arbitrary line here that our graph cannot cross. So look at the first one. If you look, our graph does not keep going up because there's some line there that our graph can't cross to make it keep going up. So we can say that it's bounded and that that line is above the graph, therefore it's bounded from above. If you look here below it, you'll notice there's some arbitrary line down there too that doesn't allow our graph to go any further down it, therefore it's bounded up below, or we can just say therefore it is bounded. All right, the second one here, you'll notice the graph keeps going up, so it's not bounded above, but the graph does not keep going down, therefore it is bounded below. On the third one, you'll see that it does not keep going up, therefore it is bounded above, but it does keep going down, so it's not bounded below, so we only say bounded above. And then on the last one, you can see it keeps going up, so it's not bounded above, keeps going down, so it's not bounded below, so we can just say that this is not bounded. So a way to ask yourself here is, guys, when you're looking at whether it's bounded or not, look at the graph, okay? And then ask yourself, does it keep going up? If no, we say it's bounded above. Okay, and then ask yourself, does it keep going down? If no, it's bounded below. And if both, then we just say it's bounded. Okay? So if we say it's bounded above and we say it's bounded below, we can just say that it's bounded. And then, of course, if it keeps going up and it keeps going down, then it's not bounded. All right, and so there's our technical definition if you'd like to read through it. But now we're going to talk about symmetry. And so when we first start talking about symmetry here, they talk about even and odd functions. And so a function f is even if and only if when the point xy is on the graph of f, then the point negative xy is also on the graph of f. So a couple ways to tell if a function is even or not. Looking at the graph, even functions are symmetric to the y-axis. That means the y-axis is going to split it in half and it could lie on top of itself. All right? And that's why they say the point xy and the point negative xy would both be on the graph. Algebraically, we're going to find that f of negative x is equal to f of x. So what that means is, so algebraically, we would plug in negative x for x and solve. Or I should say, and simplify. Okay? If it is an even function, after we simplify it, we will get the same exact equation we started with. So we're going to plug in negative x for x and simplify, and we'll get the same equation that we started with. Okay, an odd function. An odd function is, it says a function f is odd if and only if when the point xy is on the graph of f, then the point negative x negative y is also on the graph of f. So f of negative x is equal to negative f of x. So if you're just looking at the graph, an odd function is symmetric to the origin. That one's usually a little harder to see, okay? Being symmetric to the origin is harder to see, but the easiest way I can do it is I can look and see that it reflects across the x and the y axis. All right. Algebraically, what it's saying, that's that f of negative x is equal to negative f of x. So just like before, we're going to plug in negative x for x and simplify. And what we'll notice here is that all signs will change. So when you look at the signs of your terms, the positives and the negatives, the pluses and the minuses, they will all change from the original equation. All right, so let's try this. Example 7. Look at it. First, if we're trying to do this, just looking at whether it's symmetric to the y-axis or if it's symmetric to the origin, first let's check the y-axis. So I'm going to draw a line here on my y-axis. Remember, if it is symmetric to the y-axis, the left side should look just like the right side, where if I folded on that y-axis, it would lie on top of itself. And it does not here. So this one is not symmetric to the y-axis, which means it is not even. Then we got to check to see, is it symmetric to the origin? In order to do that, I'm going to pick a point. And so I'm going to pick, how about this top point right there? Oops. And so an estimated value of it is what? -1, +3. All right, so if I reflect that across the x and the y-axis, it doesn't matter which one you do first. So I'm just going to go across the y-axis here, and so that would be the point there, and then across the x-axis right here. Did I land on the graph? I did, and that new point is at 1, -3. And that's what it was saying up there when it said x, y, and then -x, -y is on the graph. So therefore, because this one is symmetric about the origin, we know that this is odd. So look at B. Even, odd, or neither. Well, let's split it in half. Let's draw in the y-axis to see is it symmetric there. Did it split the graph in half? It did. If you notice, the left side is just like the right side. If I folded on that line, it would lie on top of itself. I can also pick some points on here and check. So if I pick this point right here, which is -4, -3, and I'll look over here, I have +4, -3 also on the graph. So therefore, that also shows me that it's even, because that's what it says up there. If I have the point xy, then I'll have -xy also on the graph. So therefore, because this one is symmetric to the y-axis, we can say that this is even. So now let's check C. So first I'm going to check to see if it's even. I'm going to look at my y-axis there, and does it look like it's symmetric to it? Does that y-axis kind of split it in half and have mirror images on both sides? It does not. So it is not symmetric to the y-axis. So it is not even. Now I'm going to pick a point on here. Let's pick this one here. So if I want to see if it's odd, remember I'm going to reflect it across the x and the y-axis. Doesn't matter which one's first. So I'm going to go across the x-axis and then across the y-axis, which means that right there should be a point on my graph, and it is not. Therefore, it is not odd. It's not even, it's not odd, so we say that this is neither. All right, then to find out algebraically. So for algebraically, we're going to remember, we said we're going to plug in -x for x and then simplify it. So here I'm going to plug in -x for x, and then I want to compare it. Well, now the absolute value is a little bit confusing, but think about it like this. If I have the absolute value of a positive number and the absolute value of the same number but it's negative, are they the same? And it is. So if you think about, like, if I have the absolute value of 5 and the absolute value of -5, they're equal. So this part right here is the same, okay? And then the -2 is the same. So what we're going to do is when we do this, we compare it back to the original, and the first thing we do is we ask ourselves, let me erase this part so we have room to write it. So we ask ourselves, are they the same? And in this case we said yes, therefore we know that this is even. So let's do the same thing for b. Let's plug in negative x for x. And we're going to simplify. So here we have a negative x cubed, which gives me just a negative x cubed without the parenthesis, minus 3. I'm going to take that, compare it back to the original. Are they exactly the same? Well, the first one started out with a positive x cubed, and this one was a negative x cubed. So when we ask, are they the same? Our answer is no. Then if they're not the same, we're going to see, did all signs change? So that means every term I'm going to check. So we already said the first one changed because it was a positive x cubed, and now we have a negative x cubed. But we had a negative 3, and we still have a negative 3. So not all signs changed. So therefore, it's not the same, so that means it's not even. They didn't all change, so that means it's not odd. And if it's not even and it's not odd, then it has to be neither. And then C. Let's do the same thing. Let's see if it's even, odd, or neither. We're going to plug in negative x for every x. And so we get 2 times a negative x cubed is negative x cubed. And then here I don't have an exponent other than a 1 there, okay? If I had an exponent, guys, you have to deal with that first. But so I've got minus a negative, which is a plus. And then I'm going to simplify this piece. 2 times negative x cubed is negative 2x cubed plus x. And so let's check. Is it the same? Well, I started out with a positive 2x cubed and now have a negative 2x cubed, so no. So we know it's not even. So did all signs change? Well, we know it was a positive 2x cubed and became a negative 2x cubed. I had a negative x and it became a positive x. So yes, all signs change, which means it is odd. Alright, so that's even, odd, or neither. And then we talk about symmetry. Well, remember symmetry back in geometry is something can be symmetric to the x-axis, the y-axis, the origin, or the line y equals x. And so in order to find whether or not what this graph is symmetric to, we're going to have to check all 4. So first let's check if it's symmetric to the x-axis, which means we're going to plug in negative y for y. So I'm going to rewrite my equation, but where I have a positive y, I'm going to put in negative y. Okay? So we've got x squared plus 2 times, it's y, so negative y squared equals 6. And I want to simplify this and see, can I get it back to be exactly the same? If yes, it's symmetric to it. If no, it is not. And so we got x squared plus 2, remember exponents first, so a negative y squared is a positive y squared equals 6. And then 2 times y squared is just 2y squared, so I'm going to leave it like that. Compare this back to the original problem. Is it exactly the same? It is. So this graph is symmetric to the x-axis. But we have to check all of them. So let's check the y-axis. To check if a graph is symmetric to the y-axis, we're going to plug in negative x for every x. So my equation was x squared, so I'm going to put negative x squared plus 2y squared equals 6. We're going to simplify this, and negative x squared is x squared, and bring down the rest of it. And then compare this to the original. Is it the same? Yes, it is. Therefore, this graph is also symmetric to the y-axis. Then we've got to check the origin. For the origin, we change the sign of the x and the y. So replace negative x for every x, negative y for every y. And so we're going to get negative x squared plus 2 times negative y squared equals 6. Simplify this. And then compare it. Is this the same as what we started with? Yes, it is. So we know this graph is also symmetric to the origin. And then we're going to check the line y equals x. For the line y equals x, we're going to switch x and y. So that means now we're going to have y squared plus 2x squared equals 6. Is there any way I can get that 2 over on that y squared? Well, the only way would be to divide by it, but then it's not going to be 2y squared, it's going to be y squared over 2. So there's nothing I can do here to make this be the same as the original, therefore this one is not symmetric to the line y equals x. Alright, and so as long as you label them, this is x-axis, this is the y-axis origin, and the line y equals x, it's okay to put yes or no. Or if you want, you could write it out. You could put it symmetric to the x-axis, y-axis, and origin.